question of whether reality is made of particles or is a continuum supporting waves is a question as old as physics itself. I'm Hans Schantz, and this presentation explores wave-particle duality, particularly in the case of light. Not much is known about Democritus. In the Timaeus, Plato associated each of 5 elements, fire, air, earth, water, and ether, with a regular solid, the tetrahedron, octahedron, cube, icosahedron, and dodecahedron. The figure shows Democritus as well as a diagram by Johannes Kepler of Plato's interpretation of Democritus's atomic theory. Democritus's thinking appears to have been more complicated and subtle, however. In a lost essay from which only fragments remain, Aristotle describes Democritus's own atomic model of reality. Democritus thinks that the nature of eternal things consists in small substances, infinite in quantity, and for them he posits a place, distinct from them and infinite in extent. He calls place by the names void, nothing, and infinite, and each of the substances he calls things solid and being. He thinks that the substances are so small that they escape our senses, and that they possess all sorts of forms and all sorts of shapes and differences in magnitude. The Greek physician Galen of Pergamon reported Democritus indicted the senses, saying, by convention color, by convention sweet, by convention bitter, in reality, atoms and void. Galen also reports Democritus noted the contradiction inherent in arguing against the validity of perception while employing that same method. Poor mind, do you take your evidence from us and then try to overthrow us? Our overthrow is your fall. Democritus observed that the senses failed to provide a full and complete picture of reality, yet he also apparently recognized that it was through the senses that we acquire what knowledge we can about how reality works. Democritus's atomism influenced Epicurus. Where Democritus thought reality unfolded according to the purely deterministic actions of atoms interacting in a void, Epicurus held that occasionally atoms randomly swerve. This, in his view, was the physical basis of free will. The Roman poet and philosopher Lucretius wrote a famous poem on the nature of things, elaborating upon the ideas of Democritus and Epicurus. Lucretius extended upon the Epicurean swerve, describing a curious random movement of small dust particles. Observe what happens, said Lucretius, when sunbeams are admitted into a building and shed light on its shadowy places. You will see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of underlying movements of matter that are hidden from our sight. It originates with the atoms which move of themselves, i.e. spontaneously. Then those small compound bodies that are least removed from the impetus of the atoms are set in motion by the impact of their invisible blows, and in turn cannon against slightly larger bodies. So the movement mounts up from the atoms and gradually emerges to the level of our senses, so that those bodies are in motion that we see in sunbeams, moved by blows that remain invisible. When Lucretius's ideas were rediscovered around 1415, they inspired a lot of atomic and corpuscular doctrines of nature. In 1827, the Scottish botanist Robert Brown microscopically examined pollen from pink fairies, Clarkia pulchella, a flower first discovered in northern Idaho by Lewis and Clark in 1806. Brown noted his pollen particles immersed in water were in constant motion. The phenomenon became known as Brownian motion. In 1905, Albert Einstein presented a statistical model explaining Lucretius's observation in terms of atomic theory. Lucretius observed that clothes hung out near a shore became wet, and hung out in the sun became dry, the minute portions of moisture imperceptible to the eye. We can sense odors that we cannot otherwise perceive. Matter exists in small quantities and accumulates or decreases without being seen. All these ideas go back to Lucretius. Aristotle opposed this atomistic thinking, and his views remained doctrine for many centuries. In the 1600s, though, that began to change. Galileo first argued that the reason a pump can suck up water is not because nature abhors a vacuum, but because the atmospheric pressure can support a column of about 34 feet of water. Galileo's student, Torricelli, used a more dense liquid, mercury, to demonstrate the same effect in a smaller scale, showing atmospheric pressure could support about 30 inches of mercury, thus inventing the barometer. Torricelli postulated that we live in a sea of air, and thus the atmospheric pressure and height of the column of mercury it would support would vary with altitude. He validated his predictions with measurements of pressure versus the altitude. By 1657, Otto von Guericke perfected a vacuum pump that evacuated two 20-inch diameter hemispheres. In spectacular demonstrations, he showed that two teams of 8 horses were unable to pull them apart, but they fell apart easily when air was allowed back into the evacuated hemispheres. The Aristotelian plenum did not fade away easily, however. René Descartes' ideas remained prevalent throughout the 1600s. Descartes held a corpuscular view of reality. He argued that all space is full of particles of various kind whose motions give rise to physical effects. He also attempted to explain the motions of the planets in terms of celestial particles swirling about. These swirling particles explained, in his view, why air remains pressed against the surface of the Earth and why the planets orbit the sun guided by circular swirls of particles. His views led Descartes to some prescient insights, for instance, that heat is the rapid motion of the particles that make up material objects. In addition, of course, Descartes was a pioneer in analytic geometry. Every student of algebra is familiar with the Cartesian axes that he devised. Descartes' overall performance in physics, however, was pretty mediocre. Descartes tended to lounge about in bed, reading, writing, and thinking deep thoughts, usually rising in time for lunch. While certain of his insights, particularly his mathematical ideas, had staying power, his deductive approach to physics is at odds with the facts of reality. But Descartes' method is really reminiscent of those of modern physicists who seek to discover a theory of everything, a set of equations simple enough to write on a t-shirt from which reality may be rigorously deduced. The contemporary approach, of course, is on a more abstract level, substituting multidimensional geometric structures for nebulous notions about the perfection of God. And of course, contemporary physicists require that their theories match the experimental data. In any event, Descartes' lifelong habits of leisurely contemplation may well have been his undoing. Queen Christina of Sweden hired Descartes to be her personal tutor. Arriving in Stockholm in the middle of the winter, Descartes discovered the Queen expected him to be available every morning at 5 a.m. The stress and the cold were too much for Descartes, and he succumbed to pneumonia within weeks. Isaac Newton made phenomenal contributions to physics. In his early years, Newton speculated that the gravitational influence of the Earth might stretch all the way out to the moon. Using the experimental data available to him, he calculated that the ratio of the moon's acceleration to the acceleration of an object falling near the surface of the Earth was roughly equal to the inverse ratio of their distances from the center of the Earth squared. This suggested that the gravitational force decreased as the inverse square of the distance. Newton continued his investigations. Under the assumption of point bodies and circular orbits, Newton found his law would also yield the appropriate relation between the period of the orbit and the size of the orbit, discovered by Kepler. Real planetary orbits are more complicated than perfect circles, however. Newton was aware of Kepler's discovery that planetary orbits are elliptical. Newton demonstrated through a lengthy geometric proof that his inverse square law would yield Kepler's relation even in the case of elliptical orbits, thus tying Newton's abstract ideas back to reality. Newton even used his own and others' observations of the great comet of 1680 to verify Kepler's laws. Finally, real planets are not point masses. Instead, their mass is distributed throughout an extended body. Newton showed that the gravitational attraction of a spherically symmetric body was the same as the attraction of a point object with the same mass. With the benefit of hindsight, we can acknowledge Newton's greatness and his contributions to physics. At the time, however, the Cartesian plenums were slow to yield to Newtonian forces of attraction across a vacuum. Writing in 1730, Voltaire proclaimed, "A Frenchman who arrives in London will find philosophy, like everything else, very much changed there. He had left the world a plenum, and now he finds it a vacuum. In France, 'tis the pressure of the moon that causes the tides, but in England, 'tis the sea that gravitates toward the moon." Using Newton's methods, in 1705, Edmund Halley noted that a 1682 comet had nearly the same orbital characteristics as comets seen in 1607 and 1531. He predicted its return in 1758, but sadly did not live to see what we now call Halley's Comet, when it arrived in December of 1758. No one ever seriously questioned Newton's theory after the return of Halley's Comet, opined J.B.S. Haldane. Under the influence of Newton's successors, however, the tie between the facts of reality and Newton's mathematical abstractions began to fray. Newton explained what gravity does, but he offered no explanation for why such a force exists or how it's caused. He could not reduce his mathematical law to any more fundamental level, and he thus scrupulously avoided offering any ungrounded speculations. In a 1693 letter to the theologian and classical scholar Richard Bentley, Newton wrote, "You sometimes speak of gravity as essential and inherent to matter. Pray do not ascribe that notion to me, for the cause of gravity is what I do not pretend to know, and therefore would take more time to consider of it." Roger Coates offered a defense of Newton's gravitational ideas in his preface to the second edition of Newton's Principia. However, where Newton judiciously declined to take a stand on the cause of gravity, Coates argued that gravity was a primary quality of all bodies, akin to mass and extension. Coates further claimed that it was an attribute of all bodies. Implicitly, Coates sanctioned the idea that gravity works by action at a distance, that two bodies interact through space without the intermediary of any other agency. The connections between the evidence and the theory continued to unravel at the hands of the Jesuit mathematician Roger Boscovich, who explicitly interpreted Newton's physics in terms of point particles acting at a distance through no intermediary. Newton specifically disavowed such a view, saying in his 1693 letter to Richard Bentley that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton's own views remained hidden in personal correspondence, however, and those of his misinterpreters carried the day. James Clerk Maxwell, the famed discoverer of the laws of electromagnetics, noted in 1876, "And when the Newtonian philosophy gained ground in Europe, it was the opinion of Coates, rather than that of Newton, that became most prevalent, till at last Boscovich propounded his theory that matter is a congeries of mathematical points, each endowed with the power of attracting or repelling others according to fixed laws. In his world, matter is unextended and contact impossible." He did not forget, however, to endow his mathematical points with inertia. And now let's turn specifically to the case of light. By the middle of the 17th century, the fundamental laws of optics were well understood and lens making came of age. Galileo used a telescope of his own design to observe the heavens. The lavish illustrations of Micrographia, written by Robert Hooke and published in 1666, inspired a fascination with all things microscopic. Antony Philips van Leeuwenhoek crafted a 300-power microscope in the 1670s and made pioneering observations of microorganisms. These discoveries led investigators to ask the more fundamental questions, like what is light and how does light work? Christian Huygens argued that light was a wave. His younger contemporary, Isaac Newton, countered implicitly that light was a stream of particles. The Dutch physicist Christian Huygens made fundamental contributions to math, science, and optics. He wrote treatises on probability, timekeeping, mechanics, as well as optics. His observations of the rings of Saturn made clear that they were thin disks, and he discovered Saturn's giant moon Titan. Perhaps Huygens' greatest achievement, however, was his wave theory of light. Huygens' principle is the notion that every point on a wavefront is itself the source of secondary wavelets, which then mutually interact and interfere. You can see Huygens here with a figure from his 1690 book, Traité de Lumière, or Treatise on Light. In this figure, a wavefront AC impinges on boundary AB. Point A becomes a source for a wavelet that after a certain amount of time has expanded to S. Each successive point on the wavefront, H, impinges on the surface at K, generating a new wave that is slower below the AB boundary than it was above. The wavefront thus bends at the surface points, so the AC wavefront becomes the successive OKL wavefronts, and finally the NB wavefront. Huygens was convinced that light was a form of wave motion, and that focused light could ignite a fire proved to him that it imparted motion, for it caused the dissociation of the molecules of combustible material. Isaac Newton earned his Bachelor of Arts degree from Trinity College in 1665. Plague soon prompted him to depart for home, where he completed some of his most important work, including the fundamentals of calculus. In 1668, he earned his master's degree at Cambridge and was elected a fellow at Trinity College. Throughout this period, Newton had an interest in optics. He set up a furnace, cast and polished lenses, and devised a way to deposit metal on glass to make high-quality mirrors. Conventional refracting telescopes used lenses to focus light to an observer's eye. As light focused through the glass lenses, it suffered from aberrations. Different colors focused at different points, blurring the resulting images. Others had tried to avoid this by using a mirror to focus incident light, but then the observer would have to block the incident light to observe the image at the focal point. Newton's simple but ingenious solution was to place a prism at the focal point, allowing for observation without blocking the incident light. Newton became the Lucasian Professor of Mathematics at Cambridge in 1669. He described his reflecting telescope in a 1669 letter to Henry Oldenburg, Secretary of the Royal Society of London. In 1671, he sent his telescope for inspection by the Royal Society, and the Royal Society immediately nominated and elected him a fellow in recognition of his accomplishment. Now, Newton read Hooke's 1666 work Micrographia and became acquainted with the vibration or wave theory of light. In unpublished notes, he objected, why then may not light deflect from straight lines as well as sounds, and so forth? How doth the foremost weak pulse keep pace with the following stronger, and can it be then sufficiently weaker? Newton concluded that the largely rectilinear motion of light meant light-comprised objects he called rays. The least part of light he said, which may be stopped alone without the rest of the light, or propagated alone, or do or suffer anything alone, which the rest of the light doth not or suffers not, I call a ray of light. Newton's work became the foundation of what we would now call geometric optics, the description of light propagation in terms of geometrically defined rays that reflect from mirrors or converge or diverge through a lens. You can see a couple of simple examples from his 1704 treatise, Optics, here. Newton used prisms to divide sunlight into colors and then recombine the spectrum back into white light. He concluded, incorrectly, that this behavior was not compatible with light having a wave-like nature. This figure shows the details of one of his experiments along those lines. When Newton shared his experimental work and theories with the Royal Society in 1672, Robert Hooke, who was a strong advocate of the wave theory, sharply criticized him. White light was pure and elemental, not a combination of colors, Hooke insisted, ignoring the substantial evidence Newton compiled to the contrary. Hooke further sneered that the sum of what Newton sent to the Royal Society was to be found in his own micrographia. This conflict explains why Newton deferred the publication of his own Optics until 1704, a year after Hooke's death. In Micrographia, Hooke noted that thin flakes of mica gave rise to colors that depended upon the layer thickness. Newton looked closer, placing a convex spherical lens with a radius 25 inches in contact with a glass plate and scrutinizing the resultant colored rings. Newton explained rays of light were subject to what he called fits of easy reflection and transmission, a kind of periodic influence that the surrounding medium exerted upon the behavior of the rays. He calculated the periodicity of these fits of easy or difficult propagation based on the known spacing between the curved and flat glass. When he correlated his results to the separated colors in the ring pattern, he found values that correlate to the actual wavelengths of light. Newton used a convex lens with an optical radius of as much as 50 feet. The gentler curvature spread out the rings, enabling precise measurements of wavelengths on the order of 390 to 700 nanometers, 1/65,000th to 1/40,000th of an inch. In other words, although Newton explicitly rejected the wave theory of light, his conception of material rays required a wave-like interaction with the surrounding medium. These are some examples of Newton's rings and Newton's analysis. Ironically, although Newton was a strong proponent of geometric optics, treating light as a ray, he also became a pioneer in physical optics, describing the propagation of light using wave theory. In a sense, Newton's approach was reminiscent of modern quantum theory, treating light as a particle that nevertheless exhibits wave-like behavior or properties as it propagates and interacts with matter. Newton followed Descartes in interpreting refraction as a speeding up of light in a dense medium. The medium, in Newton's thinking, exerts a force of attraction on the ray, causing its trajectory to deflect toward the medium. The horizontal velocity remains the same, while the vertical velocity increases due to the greater attraction of the denser medium on the ray. The velocity in the denser medium is greater than the velocity in the less dense medium. In Huygens theory, on the other hand, the wavefront slows down upon entering the denser medium, yielding the exact same curvature of the direction of propagation. You can see a comparison here of Newton's and Huygens theories. The approaches may be mutually contradictory with different predictions for the velocity of light in a dense medium, but both yield the same correct result. Newton's remarkable experimental precision with optical measurements and his prestige as the discoverer of the laws of motion and an inventor of calculus lent credibility to his optical opinions. Newton declared in the opening line of the first book of Optics, "My design in this book is not to explain the properties of light by hypothesis, but to propose and prove them by reason and experiments." He He was scrupulously vague on the true nature of rays throughout optics and Principia. For instance, in his description of diffraction, he noted that rays are bent or inflected around bodies as if they were attracted to them. Despite Newton's influence, Huygens wave theory continued to have prominent advocates, including Franklin and Euler. Still, Newton's optics set a benchmark in both geometric optics, the study of light propagating as rays, and physical optics, the study of light propagating as waves. Newton's benchmark would stand for a century. Moving beyond Newton's results would require a genius of unusual talent. Enter Thomas Young. Dubbed the last man who knew everything, Young trained as a doctor, yet made fundamental contributions in several diverse fields. His work on the Rosetta Stone contributed to Jean-François Champollion's breakthroughs in translating hieroglyphics. In addition to his medical practice, he served for a time as a professor of natural philosophy at the Royal Institute. He derived a formula for the wave's speed of the pulse, figured out how an eye adjusts its focus, and developed the theory of surface tension and capillary action. We remember him here for his development of the principle of interference, that fine discovery, to use the words of his contemporary Francois Arago, which will render his name imperishable. Consider two narrow but closely spaced slits illuminated by a point source of light. Each becomes a separate source of light waves, and the total intensity depends on whether the waves add up constructively or destructively at a particular point. Young's work was very promising, but the particle theory still held sway. In 1817, the French Academy of Sciences offered a prize for the best explanation of diffraction. Ardent advocates of the particle theory of light, like Biot, Poisson, Laplace, and Gay-Lussac, were to judge the submissions, eager to find an explanation for diffraction that would avoid Young's troublesome wave theory. The fifth member of the committee was Arago. The form of the question itself appeared to prejudice the result in favor of particles. Fresnel submitted a much revised and extended essay on the application of his wave theory of light to diffraction. He explained diffraction from a wave theory perspective. Poisson scrutinized Fresnel's theory and perceived a flaw. If Fresnel were correct, the center of the shadow of a circular disk should be illuminated with a bright spot, a spot as bright as it would have been if the disk were not there at all. Poisson thought this was an absurd result, counterintuitive, and demonstrated the folly of Fresnel and his theory. Arago listened respectfully, went away, and put the ridiculous prediction to the test. Arago attached a 2 mm diameter disc to a glass plate and illuminated it. There it was, a bright spot in the middle of the shadow, just as Poisson had dismissively predicted. It would be nice to be able to describe how the dramatic result convinced the committee that Fresnel was right, and thus the wave theory overthrew the particle theory. Sadly, science does not often work that way. However, Fresnel did win the prize, and even the particle theory adherents acknowledged the efficacy of his mathematical formulas. The behavior of light in the spot of Arago defies explanation from a particle point of view. Consider what happens in cross-section. From a Newtonian perspective, one could imagine rays bent by their interactions with the disk, focusing on a particular point. But the spot discovered by Arago converged to a continuous line along the axis, not to a point. In Fresnel's theory, the waves diffract around the edge of the disk. The path length from any point around the circumference of the disk to the axis is the same, so the waves always add up constructively on the axis of the disk. It's as if the light somehow curves inward from the edge of the disk before curving outward to converge with the axis. Let's skip ahead 100 years to the development of quantum mechanics. Light was discovered to be quantized, to come in discrete lumps that were called photons. quantum mechanics was said to demonstrate that contradiction and uncertainty are inherent to reality. If we have light incident on two slits, the waves from the two slits generate an interference pattern of light and dark. The energy is quantized in those discrete little lumps, the photons, and even if the light is so dim that only one photon is traversing the two slits at a time, we still see an interference pattern. Any attempt to measure which slit the photon passes through destroys the pattern. It's as if the photon somehow is in two places at once, passing through both slits at once, so its location is uncertain. Or alternatively, perhaps the photon is taking all possible paths simultaneously and only retroactively choosing a particular path at the moment of measurement. Richard Feynman argued that all the weirdness of quantum mechanics is captured in this experiment, calling the two-slit experiment a phenomenon which is impossible, absolutely impossible, to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. In the Copenhagen interpretation, the quantum wave function collapses only at the moment of measurement. In 1935, Schrödinger constructed a thought experiment to expose the ridiculousness of that notion. He imagined that a cat is confined in an enclosure with a radioactive substance. If the substance decays, it triggers a mechanism to release cyanide and kill the cat. If it doesn't, then, of course, the cat is still alive at the end of an hour or so. Schrödinger constructed his example to highlight the ridiculousness of the concept that a quantum indeterminacy is resolved only by the act of measurement. His daughter Ruth is alleged to have said, "I think my father just didn't like cats." But there are many people who take Schrödinger's example very seriously. In the many worlds interpretation, they argue that whether or not that radioactive decay happens splits reality into two different universes, a world where the cat is alive and a world in which the cat is dead. A final interpretation is called the pilot wave theory of quantum mechanics, which we'll get to in just a moment here. In October 1927, Louis de Broglie presented a clever new idea to many of the world's top physicists at the 5th Solvay Conference on Electrons and Photons. De Broglie supposed that the photon is a discrete object with a discrete location. The photon is then guided by a wave. The wave traverses both slits and interferes with itself. The photon is carried along by the resulting wave motion and the interference pattern through one of the two slits. In my hypothesis, de Broglie explained, the wave in a way piloted the corpuscle, hence the name theory of the pilot wave, which I gave to the conception. Facing intense opposition, de Broglie was persuaded to renounce his idea in early 1928, and in 1932, John von Neumann claimed to have proved that de Broglie's approach was mathematically impossible. In the Copenhagen interpretation, all possible paths through the two slits are taken simultaneously, and the quantum waveform or wave function collapses to a particular value on detection or observation. That was the point of view pioneered by Niels Bohr and championed by Werner Heisenberg, among others. In the many worlds interpretation, all paths were taken simultaneously, and we just happened to live in the particular universe in which the result we got was the one that was obtained. And of course, the pilot wave. The quantum fields propagate through both slots, generating an interference that guides the photon along a particular energy trajectory. But in physics today, the most common interpretation of quantum mechanics was summarized by David Verman. Shut up and calculate. We have a theory that lets you get the answers, and who really cares how it works or why it works or what are the fundamentals of quantum mechanics. In 1947, Richard Feynman's graduate advisor, John A. Wheeler, a famous physicist in his own right who worked with Niels Bohr to develop the theory of nuclear fission, recruited a young physicist from Berkeley to join the faculty at Princeton University. David Bohm came well recommended, having worked with J. Robert Oppenheimer, the man who led the Manhattan Project, to develop the atomic bomb. Bohm accepted the conventional Copenhagen interpretation he'd been taught in graduate school, and Bohm wrote an excellent textbook on quantum mechanics surveying the development of the field. That work left Bohm with lingering doubts, however. In 1952, Bohm revived and extended upon the nearly forgotten de Broglie pilot wave approach. Bohm fell under suspicion for his communist views. Princeton fired him, and Bohm ended up in Brazil. After Bohm had left, Oppenheimer led a symposium at Princeton on Bohm's work. The attendees spent hours trying to debunk Bohm's juvenile deviationism. When they failed, one of the attendees reported that Oppenheimer dismissed Bohm, saying, "Since we can't disprove him, we'll just have to agree to ignore him." It took another decade before a physicist named John Stuart Bell started untangling what quantum mechanics really meant. Bell demonstrated that von Neumann's proof was invalid, and he inspired new interest in the foundations of quantum mechanics. As Bell observed, while the founding fathers agonized over the question particle or wave, de Broglie in 1925 proposed the obvious answer, particle and wave, as a solution for the question of wave-particle duality. Today, there's a small community in physics working to understand the physical basis for quantum mechanics, but they're largely dismissed by the mainstream community that would prefer everyone to shut up and calculate and ignore any physical picture of how quantum mechanics works and the fundamentals of quantum mechanics. As a young physics graduate student myself at the University of Texas at Austin, I had the great good fortune to have John A. Wheeler on my own doctoral committee. We had many long discussions. In May of 1994, I asked Wheeler about his own travels to Bohr's Copenhagen Institute, his work with Bohr developing the theory of nuclear fission, and his efforts to understand quantum mechanics. "Any place I could look for answers to quantum mechanics, I will," Wheeler assured me. A couple days later, I asked Wheeler about Bohm. He described recruiting Bohm from Berkeley to Princeton. Wheeler's opinion of the pilot wave concept? The screwdriver theory of the double-slit experiment, he called it. I wasn't sure what Wheeler meant by his screwdriver theory quip, so I pressed him for more details. He replied, "I never really studied into that business, and I really should, so I can see what's wrong with it." Many of even the most brilliant physicists like Wheeler never seriously questioned the conventional wisdom of the Copenhagen interpretation and the consensus of their peers. I never reconciled myself to the contradictions of quantum mechanics. I struggled mightily with the subject in grad school. I chose instead to focus on electromagnetics, and I went on to a successful career in theoretical and applied electromagnetics. In particular, my work focuses on how electromagnetics works, how energy moves, how it transitions between static or bound or reactive states, and radiation. Richard Feynman once observed that the simple concept, everything is made of atoms, allows a vast range of other phenomena to be integrated and understood. From that one simple principle, a whole host of physical, chemical phenomena may be inferred. You don't have to be a chemist or understand stoichiometry, oxidation and reduction, specific heat, and phase changes to be able to appreciate the basic notion of atomic theory. But atomic theory makes those complexities easier to understand by creating a simple story, a clear narrative to unify the field and explain how all the results fit together. My goal in studying electromagnetics has been to figure out how it works. I aim to make sense of the sometimes complex mathematical description. In my forthcoming book, Fields and Energy, I'll explain how the way I have figured out how electromagnetics works through the cooperation of fields and energy allows you to resolve these quantum conundrums. Where de Broglie came up with the notion of particles and fields working together as two separate entities, classical electromagnetics can be understood as the cooperation of fields and energy working together, of fields guiding the flow of energy. In that sense, the pilot wave theory is just classical electromagnetics taken to the quantum limit. All that and more will be explained in my forthcoming book, Fields and Energy. So the solution to the question of wave-particle duality is not particles, it's not waves, it's not particles with wave-like properties, it's not waves that exhibit particle-like properties. It's two separate entities, particles and waves, energy and fields, working together to give rise to physical phenomena. If your preference in reading runs more toward fiction, may I recommend my Hidden Truth series of alternate history conspiracy thrillers. Thank you for your interest. Remember to keep calm and make physics great again. And I'll be happy to answer any questions here, or feel free to contact me. Thank you very much.